So the top half of Daily Work 10, the survey questions, are mostly getting at the same stuff that we were just talking about. So do we know whether Z120 has an element of order 24?
Yes,
Based
because
on
24 is a divisor of 120.
Because 24 is a divisor of 120, it absolutely does have an element of order 24. And remember, this is because of our fantastic theorem. This is because cyclic groups are everywhere we want them to be. What was that, MasterCard or something? Discover Card? I don't know. It was one of those credit cards. Cyclic groups are everything we want them to be. In particular, every divisor of the order has an element of that order. So yes, there is definitely an element of order 24. By the way, let me push this question a little further. What is an example of an element of order 24 in Z120? How would I find it? I would need to solve the equation 24 times x is congruent to 0 mod 120. What's an example of an x which I can multiply by 24 and get a multiple of 120? How about 120 divided by 24? Because when I multiply those together, I'm going to get exactly 120, which is congruent to 0, mod 120. But 120 divided by 24 is an integer. That's why this works, right? 5. So 5 is an example of an element of order 24. But there are others, of course. How many elements of order 24 would there be in this group? You don't have to give me a number. Give me an expression. P of 24. Euler phi function of 24. So if you do your Euler phi magic, you find out that that's, I want to say 8. I think there's 8 elements. Yeah, so phi of 24 is how many elements of order 24 there would be. How many elements of order 5 are there in this group? Always do is this order indeed a divisor of the order of the group? Because if it's not, you should stop right away and say there are no elements of this order. But if it is, then you can go forward and use the Euler phi function, which is going to be 5 to the 1. So this is 5 to the 0 times 5 minus 1. By the way, when p is a prime number, what's the quick formula for phi of p? So if you hand me a prime number, phi of p is just p minus 1, which again also makes sense by the definition of the Euler phi function, because if p is prime, how many things less than p are going to divide p? Are going to be relatively prime to p, sorry.
Everything but p.
Everything but p itself, which already wasn't included. And so there's a total of p minus 1, from 1, 2, 3, all the way up to p minus 1. All of them are relatively prime to p when p is prime. So that makes sense by the definition as well. All right, then the last question. If I know phi of 10 is equal to 4 and phi of 20 is equal to 8, what does that tell me about phi of 200? Let me give away this answer.
None of the above.
None of the above. Why not?
Because the phi of 200 is 80.
So on the one hand, yeah, we could just compute phi of 200 directly. Find out that it's 80. So that's one way of answering this question. Another way that I want to make sure we all think about is there is something that we can do with the Euler phi function that we would have been tempted to do. So the second more tempting answer here, for me, would have been answer B. Why is B a tempting answer? Or under what circumstances could we do what we're trying to do in B? If they were... If 10 and 20 were prime, we could certainly do it. But in fact, there's an even more expansive category of cases where we can do it. So phi of x times y is equal to phi of x times phi of y when x and y are prime, but not just when they're prime, when they're relatively prime, as long as they don't have any factors in common, other than 1, of course. Then the Euler phi function is multiplicative, is what we call this property, right? So 10 and 20, clearly not relatively prime because they both share a factor of 2. They also share a factor of 5, and therefore they share a factor of 10. So they're not relatively prime, which is why this computation doesn't work out using the so-called multiplicativity of Euler phi. But the fact that it is multiplicative on relatively prime numbers is what allows us to do computations of Euler phi in general. All we have to do is follow the procedure that you did at the bottom of the daily work, which is, given some integer, just first of all, figure out what is its factorization as a product of prime powers. That exists uniquely by the fundamental theorem of arithmetic. Right? So what did you find was the prime factorization for 240? 2 cubed times 240. 2 to the fourth, yeah, there we go. 2 to the fourth times 3 times 5. I think you were thinking of 200 still? Yeah. 2 to the fourth times 3 times 5, right? And what's great about that is that once you have the prime power factorization, each of these prime powers is relatively prime to each of the other prime power factors. And so that means that when I take Euler phi function of this whole thing, what's going to happen? It's just going to break apart. Right. So that's why we need the prime factorization first. It splits it apart into these three pieces, and the integers inside of those pieces are relatively prime to one another. And then, to get home, we just need to know this formula for how to compute Euler phi function for a prime power. 2 to the 4, that's going to be 2 to the 3 times 2 minus 1. Phi of 3 is just going to be 3 minus 1. Phi of 5 is going to be 5 minus 1. And so you multiply that all out. What did you end up getting here? 64 natural numbers less than 240 that are relatively prime to 240. And then just to make sure we wrap up the last question, Euler phi of 54,729 is some large number. What was it? 36,468. Actually, isn't that like half? No, it's not quite half of this. So, but it's a massive number. Okay. And how many elements of this order are there in the cyclic group Z100,000? Why not? Why are there no elements of that order in the cyclic group Z100,000? Because 54,729 is not a divisor of 100,000. Yeah. I know there are some jaded people that call things like that a trick question. We call it critical thinking. Right, because there is, our fantastic theorem tells us that it goes both ways. If you give me a divisor of the order of the group, I can give you an element of that order. If you give me something that's not a divisor of the element of the group, I can't give you any element of that order. It's not possible. It goes both ways. It's a two-way street. So that's pretty much everything we need to know about cyclic groups. That every one of them is going to have the same arithmetic properties, algebraic properties. So I'm going to close with this. Every cyclic group, and I think we said this last time, every cyclic group of order n is the same as the additive group Zn. So Zn with addition mod n. And so the reason that we study these Z groups so extensively is that once we understand how the Zn additive groups mod n work, we then understand how every cyclic group of finite order works. They're all just clocks with different numbers of hours on them. Right? And the divisibility properties, the number theoretic properties of n, tell me everything that there is to know about the properties of all of the elements in the group and all the subgroups of that group and of the group itself.